Welcome to Lecture 3.4, Fourier's Sine and Cosine Series. We'll start with some motivation. When we study partial differential equations later in this class, these are called PDEs for short, we'll see problems like the following. So here's an example. Consider a metal bar of length L equals 1. Let me draw this. So we have a bar of length 1, insulated along its interior but not at its endpoints. So that means that heat can flow laterally, but it cannot escape this way. So this is a one-dimensional problem. And so one endpoint is x equals 0, and the other endpoint is x equals 1. So it's insulated, and the endpoints, because it's open at the endpoints, it's sitting in a 0-degree room. We can imagine that the endpoints, you can think of it as sitting in a 0-degree room, or you can think of it as sticking bags of ice on the end that are 0 degrees. Initially, the bar is 100 degrees, so the temperature of the bar is like this initially, 100 degrees. And what you want to do is find the function u of xt, the temperature of the bar at position x and time t. So what's going to happen here is this 100 degrees, it's going to cool off, and the temperature of their bar is going to gradually even out, and eventually, as time goes to infinity, the bar is going to be 0 degrees. Just imagine this. You have a 100-degree bar that's insulated along the interior, but not at the endpoints. It's sitting in a 100-degree room. You come back an hour later, the bar is going to be room temperature. Or it's going to be roughly, it's never going to technically exactly approach there, but it's going to, for all intents and purposes, be 0 degrees. But how does it get there? It's going to get there via this diffusion process, where at 100 degrees it flat levels out like this, and it's eventually going to go to 0. So this is what we want to understand. So this 100 degrees, this is the temperature as a function of x and time 0. That is 100 degrees. And then maybe this curve here might be the temperature, I don't know, let's say this is the temperature as a function of x at time 1, and maybe this next one is the temperature as a function of x at time 2, and so forth. And clearly, the limit as t goes to infinity of the temperature of the bar, now it's no longer a function of t, so it's going to be a constant 0 degrees. So that's the kind of word problem that we're going to deal with, and we are going to need Fourier series for this. Actually, Fourier series were basically invented to solve this type of problem. So the function u of xt, this is a multivariate function. It must satisfy the following PDE, which is called the heat equation. This equation right here. Sometimes we write this as ut equals c squared uxx for short. Now, why does it satisfy this? I will actually derive this when we study the heat equation in the next section. We'll use multivariable calculus for that and some basic laws of physics. But for now, just know that this is a basic law. It's like Newton's law of cooling. So what's Newton's law of cooling? That says that the change of temperature is proportional to the difference in temperature to the ambient temperature, say 72 degrees. So Newton's law of cooling is if you have a point mass, or if you have a cup of water, you consider that a point mass. So this is a 0-dimensional problem, and t is a function of time. Now we have a heat equation, we have a one-dimensional problem. So instead of a point mass, we have a bar that is one-dimensional, and so the temperature is no longer a function of just time, but also of position. So this is the heat equation. More on this later. Not just why this models the situation, but also how to solve this. And then we need boundary and initial conditions. So the boundary conditions say what the temperature is at the endpoints. So we said if the metal bar is sitting in a 0-degree room, then for all time t, the left endpoint, x equals 0, is fixed at 0 degrees. So the temperature at position 0 for all time t is 0. Similarly, the right endpoint, x equals 1, the temperature at that endpoint, t at x equals 1, for all time t is 0 degrees. These are called boundary conditions because they describe the temperature or the change of temperature at the boundary. And then we need an initial condition. This is what happens at time equals 0 and as a function of x. In this case, it was 100 degrees. Okay, so that's a little crash course to basic PDEs. And again, we will do this soon. And when we do, we will see that the general solution to this PDE, subject to these boundary conditions, and by that I mean the heat equation, given the fact that the boundaries are fixed at 0 degrees, we're looking for all possible functions, is given by the following. So it's a Fourier series, and then we multiply it by e to the negative c n pi quantity squared t. So think of this as like a damper. This is like a damper, or this damper or diffusion. So I'm going to say damper. So for example, if the initial, so this is before we specify the initial condition. So let's suppose I can pick the initial condition to be anything I want to. Let's suppose I fix the initial condition to be something like that. Now what's going to happen over time? So first of all, at time equals 0, if I take u of x 0 and I plug in 0 into this thing, the exponential goes away, so I get a basic Fourier series, n equals 1 to infinity of bn sine of n pi x. So somehow this function right here I need to write as a Fourier series in sine waves. And then if this is the initial temperature distribution of the bar, then think what happens purely physically as time gets larger and larger. Well, the bar is going to spread out, right? This is still going to be the hottest point, but it's going to probably a minute later, it's going to look maybe like this. And then the temperature another minute later is going to look like this. And then it's going to level out and eventually go to 0. This is the thing. The exponential function is the damper that kills it all, because this thing goes to 0. It kills the Fourier series. So to summarize, the last step of this is to plug in t equals 0 and solve for the coefficients. This is like what we do with regular ODEs. If I say this is the general solution and this is the initial condition, well, you got to plug in 0 and set it equal to the initial condition and solve for the constants. So if we do that, we plug in 0 into here, the exponential goes away, and we get a Fourier series of sine waves, and we have to set that equal to 0. Now, how do we do that? Because the function 100 is not the sum of sine waves. However, the function 100, it's only defined this on 0 to 1. We only care about this region. We don't care about things outside of that region. So what we can do is we can make this thing into an odd function like this, and we can compute the Fourier series of that odd function. And so that's what we're going to do. Now it doesn't equal 100 outside of our domain, but all we care about is our domain, because that's our bar from position 0 to position 1. We don't care about what happens outside of this. So to summarize, in order to solve this initial value problem, we must express the function f of x equals 100 between 0 and 1 as a Fourier sine series. So that is how Fourier series come up in partial differential equations and models of things like the heat equation. And that's actually how they were invented, is when mathematicians at some point needed to solve problems like this. Okay, so let's do an example. Let's express the function f of x equals 100 as a sum of sine waves between 0 and 1. So how do we do that? So here's 1. Let me draw the function. So, well, there's the function, and if we need to express this as sine waves, this thing is an odd function. So this is odd. So we have to make this thing. So what we have to do is we have to make this odd. Now again, it's only defined on 0 to 1. So let's make it odd by this is 2, by literally making it into an odd function, making it into an odd square wave, and so forth. So this is now f of x. Now this is something we can find the Fourier series of. So do you remember how to do that? So let's do it quickly. So a naught equals an equals 0 because it's odd. So bn is 2 over 1 from integral from 0 to 1 of 100 sine of n pi x over L. L is 1 dx. So this is 200 over, this is very similar to the problem that we did earlier, just scaled by a factor of 100. 200 divided by n pi times cosine of n pi x. We need a negative sign from 0 to 1. So this is 200 over n pi. Because the negative sign, I'm going to plug in 0, then plug in 1. If I plug in 0, I get 1. If I plug in 1, I get cosine of n pi, which is negative 1 to the n. So this is it. So f of x equals n equals 1 to infinity of 200 over n pi times 1 minus negative 1 to the n times sine of n pi x. So there we go. There's our function that is a sum of sine waves that is equal to 100 from 0 to 1. Now we don't care what it is elsewhere. So now that you have the motivation and the intuition, let's define these things formally. So let's let f of x have domain 0 to L. So it's defined only between 0 and L. There are several natural ways to make this into a periodic function so we can compute its Fourier series. I think I'm going to just sketch this via example, and I think you'll get the idea. So let's suppose f of x looks like this. So this is f of x. I've made it very non-symmetric. So this is defined only on 0 to L and nowhere else. So the first way that we can make it periodic is to just copy paste it. So we can just take that little window and just copy paste it like this. And we're going to call that the periodic extension of f, because it's just taking this and copy pasting it left and right. But there are other ways that we can make this periodic. And sometimes we need to do this. Like sometimes we need to make the function even or odd. So let's first do the even extension. So the even extension, so for all of these, we are going to start with the actual function. And now for the even extension, we are going to, first of all, make it even. So this is negative L over here. So to make it even, we have to reflect it across the y-axis. And now it's a function that is periodic of period 2L. So this is L. And now we make this thing periodic. So we copy paste that thing. So here we do something like that. And then over here and so forth. This is negative 3L. This is 3L. So this is the even extension. And then the other thing we could do, of course, is what's called the odd extension. So we could take this function, this little piece, we can make it odd. So we reflect it in an odd manner about the origin, and now we have this little piece, this window of length 2L, and now we can copy paste and make this thing periodic. So let's do that. So we go like this, and then we go, oops, it's hard to draw, I'm not good at this, but you get the idea. So this is the odd extension. So now this cannot be represented as a Fourier series, f of x, because it's not periodic. It's just a little blip. But the periodic extension, if we wanted to represent this guy using a Fourier series, it's not even nor odd. It's going to contain both sines and cosines. So an cosine of n pi x over L plus bn sine of n pi x over L. However, the even extension, because we have forced it to be an even function, this is only going to contain cosines. So the Fourier series of this is just going to be a naught over 2 plus the infinite sum of an cosine of n pi x over L, and just that. Now, I should say these ANs are not necessarily going to be the same. So let me put primes here, A naught prime and AN prime. And finally, this last one, because this is an odd function by construction, the Fourier series of this guy is just going to contain sine waves. So it's going to be n equals 1 to infinity of Bn prime sine of n pi x over L. And again, I'm using prime because it's not the same Bn's as up here. Okay, so there are several natural ways to make this function periodic, and here's what we're going to do. We are going to define, or given this function, we're going to define the Fourier cosine series of f to be the Fourier series of the even extension. So this is the Fourier cosine series of f, and this is the Fourier sine series. So the Fourier sine series of f of x, that is by definition the Fourier series of the odd extension. So here it is formally. Let f of x be a function defined from 0 to L. The Fourier cosine series of f is the Fourier series of the even extension of f, and the Fourier sine series of f is the Fourier series of the odd extension. So by definition, the Fourier cosine series, A naught is 2 over L from 0 to L times f of x dx, and AN is 2 over L from 0 to L times f of x cosine of n pi x over L. Because the function is even by construction, we have formulas for A naught and AN, and we can always integrate from 0 to L and double it. In the Fourier cosine series of f, then this being an odd function, Bn, and let me just say that the Bn's here are 0, and for the Fourier sine series, A naught and AN are 0, and Bn is 2 over L times the integral from 0 to L f of x sine of n pi x over L. So I want to make this difference very clear. It is very important, and for whatever reason, students seem to have trouble with this distinction. I cannot just give you a function and say, compute the Fourier series of this, and now compute the Fourier cosine series or the Fourier sine series. These are different things. If I give you a periodic function, so given a periodic function f of x, I can tell you to compute the Fourier series of f of x. That makes sense. It does not make sense to say compute the Fourier cosine series or the Fourier sine series. Now, it might just be that the function, the Fourier series, only contains cosine terms or sine terms. But the difference here is if I tell you to compute the Fourier cosine series or the Fourier sine series, the function I need to give you has to be a fragment. So I can give you a periodic function defined on the whole real line and say compute the Fourier sine series. Or I can give you a piece of a function defined on a little interval, say from 0 to L, and I can say compute the Fourier cosine series of this, or compute the Fourier sine series of this. I can't mix them. Does that make sense? Please make sure that you get this subtle but important distinction. We'll conclude with an example. Let's let f of x be equal to x, defined on 0 to 1. So let me sketch that right here. That's easy to draw. So that's this little function. This is f of x. Let's compute the Fourier sine and cosine series of x. So I'm asking two different things. Compute the Fourier sine series and compute the Fourier cosine series. So let's do these one at a time. Let's do the sine series first. Obviously, all the ANs are equal to 0. And before we start, let me sketch what this looks like. So the Fourier sine series is the Fourier series of the odd extension. So here's the function. So the odd extension, think of this as a two-step process. Step one, make it odd. So we take this little piece and reflect it about the origin, and we get, if you want to think about it, reflected about the y-axis, then the x-axis, you can do that too. Or just force it to have odd symmetry. And now this is the window that we're going to copy-paste indefinitely. So put that there, and we put that there, and we get a sawtooth wave. So we've actually done something just like this, I think, on the previous lecture, or was it the lecture before? It was fairly recently. Okay, so here, Bn is the Fourier series of this guy. So it is 2 over L, so 2 over 1 times the integral from 0 to 1 of f of x is x times sine of n pi x dx. Okay, so this is integration by parts. So let u be equal to x, du equals dx, dv equals sine of n pi x dx, and v equals 1 over n pi times cosine of n pi x. And I always have to think, negative sign or not. When I take derivatives, I don't have to think, but when I take antiderivatives or integrals, I always have to think about whether that sign should go there or not. Okay, so let's go. So this is equal to 2 times u times v, so that's negative x over n pi cosine of n pi x evaluated from 0 to 1 minus v du. So that's v du. So minus negative, let's make that positive. And let's put the 1 over n pi out in front of the integrals because I like doing that. And we get cosine of n pi x dx. Now you may remember from a couple of lectures ago that this integral is going to be 0. And if you don't remember that, or here's how you can see that. I'll show you two ways. Well, first of all, if you take the integral of this, you're going to get sine of n pi x divided by n pi. But the sine part, when you plug in 1 into sine, you get sine of n pi, which is 0. And when you plug 0 in to sine of n pi, you get 0, n pi times 0. So both of those are going to give you 0. Equivalently, you can think of the function cosine of n pi x is literally just a cosine function that cycles n times between 0 and 1. So the area under the curve, well, not as I've drawn it, but in theory, the area under the curve should be 0 because everything cancels out. So I'll just say right away that this thing is equal to 0. You can check if you don't believe me. And now let's compute this. So when we plug 0 into here, into x, that goes away. So we only have to worry about when we plug 1 in. So here we get negative 2 times 1 over n pi times cosine of n pi, which is negative 1 to the n. So this is what Bn is. So in other words, the Fourier series is n equals 1 to infinity of negative 2 over n pi times negative 1 to the n times sine of n pi x. So this is the Fourier sine series of this function f of x. Let's now compute the Fourier cosine series. I don't think we've done this one before. So before we actually do this, I want to sketch what the Fourier cosine series looks like. So I'll do that over here. So the Fourier cosine series, so here's that function, defined on 0 to 1. And now how do we compute the Fourier cosine series? Well, let's sketch the even extension. So think of this as a two-step process. Step 1, take this function, make it even, reflect it across the y-axis. So this is our window. Now step 2, make this periodic. So if we make this periodic, now we get this guy, and this is a, what do you call it? A triangle wave. So this is the even extension. Let me write up top that this is the odd extension. So when I say compute the Fourier cosine series, we're computing the Fourier series of this guy. Okay, so the cosine series, it's b, so by definition bn is equal to 0 because this is an even function. Now a naught, well, a naught is by definition 2 over L times the integral from 0 to 1 of the function x dx. And what is that? Well, before we do that, let me just remind you that we know something about a naught. We know that a naught over 2 is the average value. And what's the average value of this function? It goes up, it's linear, piecewise linear. The average value is clearly, so this is 1, is clearly 1/2. So I'm going to say, or we know, note that a naught over 2 is 1/2, and this is the average value. So we know this. In other words, if we compute this integral, we should get that a naught equals 2. Or sorry, a naught equals 1, because a naught over 2 equals 1/2. So this thing should be equal to 1. And you can tell it, you can see that it is. Okay, now let's compute an. So an is 2 times the integral from 0 to 1. Let's see where, of the function is defined on 0 to 1. It's x, so x cosine of n pi x over L, L is 1, times dx. So this is also integration by parts. Let me get rid of those equal signs because I'm going to say let u be equal to x, du equals dx, and then dv equals cosine of n pi x, and v equals 1 over n pi times sine of n pi x. And now I do not need a sign there, S-I-G-N. Okay. Oh, and I should probably say this is dx. Okay, so integration by parts, this is 2 times u times v, so that's x times this sine, so that's x over n pi times sine of n pi x from 0 to 1. So up here, the sine series, this did not go away because we had a cosine, but this went away because when we integrate it, we got a sine. Now here we have sine of n pi x. We plug in 1, we get sine of n pi, which is 0. And when we plug in 0, we get sine of 0 times 0, if it's extra 0. So this whole thing is going to go to 0. Now, so that's uv minus v du. So v du, so minus 1 over n pi times the integral from 0 to 1 of sine of n pi x dx. Okay, so now is this going to be 0? Now I claim it's not going to be 0. Let's think about why that is, because if you integrate sine from 0 to sine of n pi from 0 to 1, sine of pi, you get a non-zero area here. See that? So this is sine of what is it? Sine of pi x. However, notice that sine of 2 pi x. So this is sine of 2 pi x. And I'm going to do a couple more of these. I think I'm going to do it to the left. What's sine of 3 pi x? So this area is going to be equal to 0. Sine of 3 pi x, that's going to be, I don't know if I can do this. So there we go. So that is going to be non-zero. So this is sine of 3 pi x. And sine of 4 pi x, so that is going to be 0. So do you see the pattern? So just by looking at this, this integral is going to be 0. Well, let's write sine of 4 pi x. So all of these guys, these integrals are going to be equal to 0. And these are going to be non-zero. Okay, so just an observation that we hopefully will verify mathematically when we do this problem. So let's integrate this. Let's put the 2 out here, or let's bring the 2 inside, or bring this out, doesn't matter. I'm going to write this as negative 2 over n pi, and now we're going to integrate this. We get a cosine, and we divide by n pi again, so 2 over n pi quantity squared. And now we get a cosine of n pi x from 0 to 1. But when we integrate sine, we get a negative cosine. And again, I have to think of this as when we differentiate cosine, we get a negative sign. So I'm going to make that a positive. And now let's plug this in and let's see what we get. So cosine of n pi x is cosine of n pi is 1. Let's hold on. That's negative 1 to the n, and then cosine of 0 is 1. So this is 2 over n pi squared times negative 1 to the n minus 1. And if you prefer, we can write this as two cases. When n is even, this is 0. So this is 0 when n is even, and that is exactly what we verified right there. That's good, as it should be. And this is, when this n is odd, this becomes negative 1 minus 1, that's negative 2. So this is negative 4 over n pi squared when n is odd. So that's the area under the curve, the signed area under these curves. Okay, so that means that our Fourier cosine series is f of x equals a naught over 2, which a naught over 2 is the average value, which is 1/2. 1/2 plus the sum from n equals 1 to infinity of 2 over n pi quantity squared times negative 1 to the n minus 1 times cosine of n pi x. So this is the Fourier cosine series. Compare that to the Fourier sine series. The Fourier sine, we started with a little piece of a function. The Fourier sine series is the ordinary Fourier series of this sawtooth wave, the odd extension, and the Fourier cosine series is the ordinary Fourier series of this triangle wave, the even extension, and that is this guy. So just one last thing I want to mention is that this is the first one of these we've seen where all the coefficients are negative. Think about that. Does that make sense? So this function, you look at it, oh, it's above the x-axis. It should be positive, right? Well, not so fast. I claim that if we think about this in the right way, we will see why these coefficients should be negative. So let me draw a cosine wave. I'm kind of running out of room here, so I'll extend this. Now, I have an axis right here, a natural axis with. So what does a cosine wave look like? A cosine wave looks like this. And what we have here looks like sort of that thing, but cornered, but flipped upside down. And how do you flip a function upside down? Well, you take its negative. So it makes perfect sense, if you think about it, that this function, if built out of cosine waves, should be built out of negative cosine waves. So yes, it makes sense that these things should be negative. Okay, so in the next lecture, we will learn about the complex version of Fourier series, and so that is how to write a periodic function using not sines and cosines, but complex exponentials. So we could just do that using Euler's formula, get a simple derivation, but I think it's worth looking into vector spaces again and to what an inner product means when we have a complex vector space. And then we will rederive those formulas from scratch. So it's a lot of fun. Stay with us.